if you have received one reminder in your screen, it means that you have 5 minutes to the final of your talk. Please feel free, and thank you very much again.
Okay, so can you hear me now?
Yes.
Okay, perfect. I hope the connection is working well. So thank you, Professor Dausti. I mean, it's a pleasure for me to be here in the this special event with young people and with this doctorate program that I saw in the initial presentation, that is a great opportunity for the students and for the young researchers. So thank you for the invitation. Thank you for letting me to give this this talk and to show what is our last results in the field of bioimaging. I have a strong relation with Brazil, and most of the research we have done has been obtained in cooperation with the group of different groups in Brazil, but mainly with the group of Professor Carlos Jacinto in the Universidad Federal de Alagoas. So I want to mention that speaking here for Brazil is a pleasure for me. I also in my lab we have been there have been many Brazilian students doing the PhD, and I have to say that I am super happy with them. Okay, so today I'm going to work about silver sulfite nanocrystals, and that's a typical fluorescent nanocrystals that are probably the best in the world for bioimaging and biosensing. And that's why this is the title of my talk, the Pelé in vivo imaging and sensing, because it's the very best material for bioimaging. So first, before I forgot, I have to say that I have to acknowledge many people and many funding agencies, because this work is between physics and biology and medicine, because we are working on the preparation of materials that are finally being used for biomedical applications. So when you are working in this kind of interdisciplinary work, you have to work with many people, and you need many colleagues that will help you in this kind of work. You need people working in chemistry, on physics, in biology, in the animal center, in veterinarians, in medical doctors, and so on. Okay, so what is the I don't know, can you see now? I want to remove this, but I don't know how to do that. Let me check one moment. Let me check one moment. Okay, can you see the screen now?
Yes, Daniel.
Okay, so what is fluorescent imaging? Fluorescent imaging is a technology that is designed to get an image of the body, of organs or tissues, by using fluorescence, I mean using light, to get the image of the tissues of the organs. For that, we use nanoparticles with the contrast agents, because when you irradiate the tissue of your body, typically you don't get any particular emission, because in principle our tissues are non-fluorescent. This is not true, but the fluorescent efficiency of our tissues is very low. So if we want to use light to get image of the tissues, we need to incorporate something inside the tissues that will give us contrast or will give us some output light. Okay, so this is basic scheme. We are planning to use light, excite tissues, and collect fluorescence that is going to be used to build up fluorescent image of different things or different tissues. Okay. Why we are working on that? Why we are interested in developing new technologies using light for bioimaging? Because if you go to the hospital, there are many different technologies that can be used now for bioimaging. You want to see your bones, or you want to see a tumor. There are many technologies in the hospital that are already working. Why we are working on a different alternative? Okay, For example, you have different techniques for bioimaging: magnetic resonance, positron emission tomography, which is nuclear medicine, X-ray computed tomography, or ultrasounds. You look at which of these techniques are using non-ionizing radiation. I mean, which one are using radiation that is not bad or is not dangerous for the tissues? Fluorescent imaging, magnetic resonance. Positron emission tomography, no, because it's using radiation, it's using radiative tracer, and X-ray, no, because it's using X-rays. Okay, sorry. What about the cost? Okay, making or getting image by using fluorescent imaging is quite cheap. You just need a laser and a camera, digital camera. Magnetic resonance is quite cheap, quite expensive, as well as nuclear medicine. X-ray tomography is not so expensive, but it's true that the apparatus is quite expensive. And ultrasound is quite cheap, but not as cheap as using one laser. Which of these techniques allows you to perform real-time imaging? Magnetic resonance, no, because you need a long time to get the image, and also you will need some post analysis of the data, positron emission tomography as well, and X-ray tomography as well. So there are no fast methods, okay? But fluorescent imaging is quite fast. What about the penetration depth? I mean, how deep can go into the tissues? With fluorescent imaging, as we will see later, I mean, using light to get image of your body, you can penetrate, but not more than centimeters. This is clearly the drawback of this technique when you compare with magnetic resonance or nuclear medicine or X-ray computed tomography, which you can get the penetration of tens of centimeters. Okay, so what about resolution? In this case, because you are using light, with fluorescent imaging, you are using radiation of short wavelength, and you can have a quite good resolution, could be of tens of microns. When you go to magnetic resonance or to nuclear medicine or to X-ray computed tomography, the resolution is more close to centimeter than to millimeter. Okay, so if you look at this table, you can see that fluorescent imaging is good because it's using non-ionizing radiation. It's quite cheap. You can get real-time image in real time, and the resolution is quite good. The only drawback is the penetration depth. Okay? So this is the motivation. Okay, and of course you can do molecular imaging. It means to detect specific molecular targets of cells and tissues. Okay, so this technique, fluorescent imaging, is quite, let's say, quite promising technology in respect to other technologies that are being used in hospitals actually nowadays. Okay, the only drawback, as I said, is the penetration depth. How we can solve the penetration depth, or why the penetration depth is not good when we are working with luminescence or fluorescent imaging? The problem is the tissues. The tissues, here you can see that the skin or the hemoglobin and the fat or whatever, they absorb strongly in the visible. That's why we are not transparent. Okay, the light is not propagating through our body. But this is true, but this is especially true in the infrared. But in the infrared, the visible, in the far infrared, there are some spectral regions where the tissues are partially transparent. These are what we call infrared windows, biological infrared windows. There is the near infrared window 1, near infrared window 2, and near infrared window 3. The one is going up to 980, from 700 to 980 nanometers. The second biological window is from 1 to 1.4 microns, and the third biological window is from 1.5 up to 1.8 microns. What happens in this spectral range? In this spectral range, the light can propagate through the tissues, and you can use that to obtain an image of internal organs, for example. If you think what happens when you put your hand in front of a red light, you can see even your bone, okay? Because the red light is propagating through the tissue, and you can see clearly inside your finger. Or you can, when you put your finger in front of a white light, you can see that only red light or infrared light is propagated to the wound. So if we want to improve the penetration depth of fluorescent imaging, we have to move, or we have to start working in one of these biological windows, okay? With that, when we work in this spectral region, we can get much better penetration depths, and we can start to get image of organs that are 1 or 2 centimeters below the skin. So with this advantage, by using infrared light, and then by being able to get into the tissues with the light, we can get information about skin process or skin properties of the skin, or even subcutaneous tissues. We can also get image of the bones, in particular in some parts of our body. We can get information about the muscles or the breast tissue, for example, okay, or even the brain. So this penetration depth, I mean, when you manage to get a penetration depth of 2 centimeters, this makes possible to get image of different organs and different parts of your body. And this is the interest of this technology. The problem, of course, is that you need an optical contrast element or optical proof, or a contrast proof or contrast element that gives you light in this spectral region. Okay, you need to have some components, some nanoparticle that emits in the infrared. So when your nanoparticle is inside your muscle, is inside your brain, you can collect the light generated by the nanoparticle. Okay. Okay, so with this, I mean, if we have these nanoparticles emitting in the infrared, we will be able to get image of the tissues. It's like putting your light from inside your body, so you can get an image of your tissue or your body. This is okay. So with that, you can get image. You can inject your nanoparticles in the vein, and then you can make a picture of your arteries, or you can inject in the muscle and you can get a picture of your muscle. So then you can do imaging, okay? But not only that, you can do sensing, okay? And the most famous example of sensing for in vivo applications, that is in which we have been working within the last 10 years, is luminescent thermometry. Luminescent thermometry is the technology that allows you to get information about the temperature of a nanoparticle from the analysis of the emission spectra of those nanoparticles. If you have a nanoparticle that is giving you a luminescent spectra, and the luminescent spectra change a lot with the temperature, by analyzing the luminescent spectra, you can get information about the thermal or the temperature of the nanoparticle, okay? The temperature of the nanoparticle. So for example, here you have different examples of how you can measure temperature depending on your nanoparticle. Some nanoparticles emit light. The intensity of the emitted light depends on temperature. So if you register the emitted light, you can get information about the temperature of the nanoparticle. Some other nanoparticles, like the quantum dots, they shift the emission spectra when you change the temperature. In this case, you can get information about the temperature of the nanoparticle by measuring where is the center wavelength of this band. The ratios on some particles, they show 2 bands, and then the ratio between these 2 bands change with temperature. So you analyze the ratio between these 2 bands, you can get the information about the temperature of the nanoparticle. If your nanoparticle is in the brain, for example, you can get information about the brain temperature. If your nanoparticle is in the liver, you can get information about the liver temperature. And also the decay time, I mean the fluorescent lifetime of the nanoparticle. If the fluorescent lifetime of the nanoparticle depends on the temperature, by recording the fluorescent decay time, you can measure at which temperature is the nanoparticle. And what is super important here is that you are using light to measure the temperature. You are not using a thermocouple that is in contact with your animal, or you are not using a thermometer that is inside a living cell. You are using light. Means that it's a contactless method. It's like wireless method, okay? And this method has been used from the last years in a very challenged application. For example, in this work, authors were able to see the temperature inside a living cell by analyzing the luminescence of the nanoparticles, and they were able to see how the cells are heating with a magnetic field, okay? And also in our group, we were able to measure the temperature of an internal organ of an animal by using luminescent nanoparticles. And because we can record in a very fast way, we can do a real-time imaging, okay? So this is a method to measure the temperature of internal organs without touching anything, without contact, okay? Okay, which is the nanoparticles we are going to use? This is let me introduce our old friend, silver sulfide nanoparticles. Silver sulfide nanoparticles are semiconductor nanoparticles that they show different advantages that make them especially suitable for bioimaging. The first thing is that they have no heavy metals. They have not cadmium. They have not toxic materials. So in principle, and at the end, they are like very biocompatible nanoparticles, because the absence of heavy metals makes them suitable for application. Okay, they have no toxicity, cytotoxicity. Okay, the emission is in the infrared. When you measure the emission of this semiconductor nanocrystals, this is the emission band. This is a very broad band with a maximum around 1.2 microns that is just in the middle of the second biological window. It means that the luminescence generated by these nanoparticles will propagate through the tissues without attenuation. So we can use that for in vivo imaging. And finally, what is super interesting is that the emission properties of these nanoparticles are super temperature dependent. So you are able to measure the emission spectra for silver sulfide nanoparticles inside an internal organ. You can see that the emission spectra depends on temperature. So you can measure the intensity, you can measure the peak position that also changes with temperature of the rate or the ratio between emitting light. And then you have the emission spectra of these nanoparticles. You have this calibration curve that you have here. You can measure the temperature of the nanoparticle. Okay, so they are very good emitted, and also they are quite good temperature sensors. Okay. Okay, let me illustrate what kind of things you can do with this silver sulfide nanoparticles. First thing you can do is high resolution in vivo imaging. This video you have here, there is a mouse, and we are injecting through the tail venous. We are injecting the nanoparticles, okay? And then you get the silver sulfide nanoparticle. And this is the fluorescence. Let me reproduce. This is the fluorescence generated by the silver sulfide nanoparticle. So you have the animal, and then the animal is being illuminated by the diode, and we are collecting the emitted intensity generated by the nanoparticles inside the circulatory system. And you can see here, you stop the video, you can clearly see, you can distinguish the veins, the arteries, and also the heart here is the liver. And so you can make an internal picture of the animal with a super high resolution. And for that, we are using a diode and an infrared camera, not more. Okay, so this image is a representative example of what we can do with these nanoparticles. We can penetrate very well into the tissues, so we can get image of internal organs. Look here how we are getting an image of the liver, and the heart is here, and these are all the vasculature going to the brain, and so on. Okay. Okay, what we can do with that? Okay, the first thing we can do is molecular imaging. For example, I show you here the sample on molecular imaging of the infarcted myocardium infarcted tissue or of heart after heart attack. Okay, so what happens when you have a heart attack or you have an infarcting? What happens is that the area that is affected by the infarction and the occlusion of the infarcted is modified. You produce an ischemia. And because of that, the cells of the myocardium express this gene, okay, the AT1R. So you have silver sulfide nanoparticles that are decorated at the surface with the antigen, okay, with the antigen, then nanoparticles that are going to be injected in the tail will be accumulated in the tissue that has resulted damage due to the infarct. So we are going to get a molecular image of the infarct by using functionalized nanoparticles. And for that, you are going to use light and not other ionizing radiation. So the idea is clear. We are trying to, in this project, we were trying to detect infarcted tissues in the myocardium. So we induce an infarct in the animal, and after the infarct, we inject the nanoparticles. The nanoparticles were decorated, attached to this gen 81R that is characteristic of myocardium after infarct. And this is the fluorescent image we obtain. When you induce infarct, and then you induce with non-functionalized nanoparticles, or nanoparticles without this antigen here, nanoparticles are accumulated in the liver and in the spleen, but not in the heart. Okay, there is not molecular accumulation or molecular imaging of the heart. Okay, if we repeat the same experiment, we induce an infarct and we inject these 81 functionalized silver sulfide nanoparticles, what happens is that the nanoparticles are being accumulated at the heart of the animal due to the presence of the infarct. So with this technique, and we are using only light, and we are using diode light for excitation, and we are using the luminescence of the nanoparticles for image reconstruction. And you can see that we can get a clear image of the infarct using this functionalized nanoparticle. This is molecular image. Another thing that we can do with these nanoparticles is that, as I told you, they can be used to measure temperature. So in this case, we combine these nanoparticles with magnetic nanoparticles. And you know that magnetic nanoparticle are nanoparticles that can generate heat if they are inside a magnetic field, an alternating magnetic field. So the idea is to monitor the temperature of the magnetic nanoparticles by using the luminescence of silver sulfide nanoparticles that are nanoparticles that, as I told you, they produce emission spectra that is strongly dependent on temperature. So what we did is we inject these nanoparticles, these capsules or hybrid systems. We combine silver sulfide nanoparticles that are going to be our nanothermometers. We combine with magnetic nanoparticles that are going to be our nanoheaters, and we inject in the animal. The animal was placed inside a magnetic source, and this magnetic source is providing high frequency magnetic fields. So we expect the magnetic nanoparticles to produce heat, and we are going to use the silver sulfide nanoparticles to calculate the temperature. And this is what we have. This is the animal. This is the picture. This is the luminescence generated by the silver sulfide nanoparticles with the magnetic field off and with the magnetic field on. And you can see that when we switch on the magnetic field, there is a decrease in the intensity because, as I told you, these nanoparticles, temperature or the intensity of the emission spectra decrease with temperature. So when we switch on the magnetic field, we increase the temperature, and then we decrease the emitted intensity. And by knowing the degree of reduction of emitted intensity, we can build up the thermal image. And this is the thermal image of this subcutaneous injection. And we can see that the temperature induced by the magnetic field is as low as 3 Celsius, but we are able to measure. So magnetic field is heating is making the magnetic nanoparticles to heat, and we are registering the induced heated or the temperature increase by using the silver sulfide nanoparticles. Okay? And this is done without touching the animal, okay, just using light. One important thing is that these results makes possible to monitor in real time the temperature during magnetic hyperthermia treatments, okay? That it was something that was impossible without this technology, okay? Okay. Okay, what happens here? Okay, the other thing, one thing that I wanted to, the other result that we have obtained is that we have used these nanoparticles for controlled hyperthermia. Okay, what is an hyperthermia treatment? Sometimes temperature, when you increase the temperature, you know that you kill the cells. Okay, that's true, and that's why it's not good to have fever. I mean, you heat your body about 42 degrees. Is super dangerous for all the cells in your body. So that's why we have a thermoregulation process. So thermal therapies are those therapies based on increasing the temperature of the tissues to treat some disease or some problems. The most common is the cancer. When you have a tumor, if you are able to hit the tumor locally, you can treat the tumor and you can remove it. In this work, what we do is, okay, when you excite the silver sulfide nanoparticles, these nanoparticles produce luminescence, also produce heat, okay? Luminescence is strongly dependent on temperature, okay? And you have different parameters to measure the temperature. You can measure by the position, or by the ratio between two bands, or by the intensity, okay? The important thing is that you have a nanoparticle that is heating and is also emitting light that can be used for thermal reading. Okay, so this is what so then in principle we can use these nanoparticles to treat a tumor, because we inject the nanoparticles into the tumor and then we hit the tumor and then we kill the tumor. At the same time, we are collecting the luminescence and we are calculating the temperature of the tumor. That's important because we want to control the temperature at which we are hitting the tumor, because we don't want to create damage in the surrounding tissues. Okay, so this was the idea. We inject the nanoparticles, the cells, the tumoral cells, so the tumor has nanoparticles inside. We excite the excitation, create heat, and then the luminescence from the tumor can be analyzed and can give us different thermal readings. Okay, and these are the results. Okay, when we have the tumor with the silver sulfide nanoparticles and we illuminate the nanoparticles, the temperature of the tumor hits a lot, and the temperature of the tumor is almost close to 60 degrees. Okay, the resolution we have in temperature determination of the tumor is 0.5 degrees. When we repeat the same experiment without in the surface, by looking at the surface temperature with a thermal camera, we can also see the heating, but it's lower than the temperature inside the tumor. That's something that was expected. Okay, and then when we repeat the experiment with a nanoparticle, you can see that the tissue heats, but not too much. Okay, what we have here, we have performed all these experiments in different animals in different conditions, and we observed that when we have the tumor with the silver sulfide nanoparticles, this is this green data, and we apply the laser treatment, then we can see that the tumor disappears. Why? Because we have heated a lot the tumor, we have destroyed the cells of the tumor. Okay, these are the pictures that we have here of the mice before and after the treatment of the tissue. So what we demonstrate here, of course, if we apply the same treatment without silver sulfide nanoparticle or without laser, okay, we observe that the tumor volume is continuously growing, and after 15 days the animal is dead. Okay, so with treatment with silver sulfide nanoparticles, we were able to destroy the tumor because the heat generated by the silver sulfide nanoparticles, it means that the silver sulfide nanoparticles were able to kill the tumor at the same time that we were measuring the tumor with in a very precise way. Okay, but as far as I told you, up to now, it means that all the things that related to silver sulfide nanoparticles are good news. The silver sulfide nanoparticles are non-toxic. Silver sulfide nanoparticles are emits in the infrared. Silver sulfide nanoparticles can be used for thermal reading. Silver sulfide nanoparticles can be functionalized to detect specific tumors or specific tissues, so we can do molecular imaging. So there is nothing bad in silver sulfide nanoparticles. This is true. It's a shortcoming. Quantum yield, the quantum efficiency, is typically below 1%. It means that they are not very bright. It means that if you want to obtain one emitted photon in the infrared, you want to absorb at least 100 photons of PAM radiation. So the nanoparticle gets 100 photons and is able only to emit one single photon. So it means that it's not very efficient, especially if you compare to other semiconductor nanocrystal like PPENGFIS, and they have a quantum yield between 10 and 80%. So, I mean, they are not efficient. Nanoparticles because you need a lot of PAM radiation to generate luminescence. Okay, so we need to change the way in which we are preparing the nanoparticles to improve the brightness. Okay. Okay. So this is the typical method of thermal decomposition. Is the typical method that we are trying to develop for improving the brightness of these nanoparticles. And the idea is to modify this traditional method of synthesis to improve the silver sulfide and the quantum yield of silver sulfide nanoparticle. In particular, what we are doing here in this work is we have two precursors for thermal decomposition. These two compounds, that is oleamine dodecanidol, these two compounds, and we are going to work by changing the ratio between these two compounds to try to improve the properties of the silver sulfide nanoparticles. Here you have the TEM image and the compositional image of the silver sulfide nanoparticles. When you change the concentration of dodecanediol, I am not a chemistry and physics, sorry, dodecanediol from 0 to 1. So you are changing or you are tuning the properties in which you are synthesizing the silver sulfide nanoparticles. And this is the results. When you plot the quantum yield, it is clear that you can improve the quantum yield by changing the composition of the reactor. Okay, so this is one way to improve, but the numbers are not super high. It's 2%. So it's true that we started from 0.01% of quantum yield or quantum efficiency, and you improve up to 2%. Okay, it's not too bad, but it's not enough. But what happens? Why is this happening? I mean, why we have this maximum in the quantum efficiency or in the brightness? You look at in detail to the TEM pictures and to the compositional picture, where this is green is red is silver and green is sulfide. Okay, is sulfide. Okay, what happens is that for this particular composition or this particular synthesis condition, you have very, very homogeneous nanoparticles. Okay, if you compare here, they are less homogeneous than here. Okay, here for very low and very high contents of dodecanidol, you have inhomogeneous nanoparticles. But when you go at this condition, you have very nice nanoparticles, very homogeneous ones, and that's why you have reduced the number of defects inside the nanoparticle for these specific conditions, and then you can have a much better fluorescence intensity. Okay, these are the nanoparticles. These are the nanoparticles that we have synthesized by this method. You can see that the composition between silver and silver sulfide and silver sulfide composition between the different elements is quite homogeneous. Okay, and we have some silver core surrounded by silver sulfide, which we call with heterodimers, and this seems to be because the best condition to reduce the number of defects and to improve the luminescence of the system. Okay, so then you can get a quite high luminescence intensity. Another method to improve the brightness of the nanoparticles is by sonication. So you prepare you grow your silver sulfide nanoparticles, and then you perform a very strong sonication process. When you have sonication, you increase or you deliver a lot of energy to the solution. So you create a very high power vibrations, and those vibrations improves the properties of our nanoparticles. Okay, so this is what we have depending on the time that we are applying the sonication. And then before sonication, the emitted intensity was low, but as we are applying sonication to the nanoparticles, the intensity generated by those nanoparticles is increasing a lot, okay? Also the lifetimes, because the lifetimes are longer as you reduce the number of defects, okay? Here you have the sonication time as a function of the intensity, emitted intensity on the dynamic radius as a function of time. And you can see that when you sonicate the nanoparticles, you introduce a lot of vibrations to the nanoparticles, then the intensity generated by the nanoparticles increase a lot, okay? But at the same time, the size of the nanoparticles reduces. Why? Because you are breaking clusters of nanoparticles. So when you sonicate, you induce a strong vibration. Let's suppose that you have two nanoparticles like this that are agglomerated. When you sonicate, you separate the nanoparticles and you go from a very big nanoparticle to a smaller nanoparticle, okay? And also you look at here at this point, also the nanoparticles becomes more homogeneous, and the content of sulfite or sulfur is reduced, okay? The good thing is that when you perform the strong sonication, you are removing some of the material at the surface of the nanoparticles. It's illustrated here, okay? So what you do is you remove the defects of the surface, okay? And then you clean the surface of the nanoparticles, and then you make them brighter. It's like that, it's like washing them, okay? So you have the nanoparticle, and you have a lot of defects on the surface, and the defects are killers of luminescence. So when you have a nanoparticle with a lot of defects on the surface, the nanoparticles is not emitting well, because those defects at the surface are absorbing the emitted radiation. If you remove that, in this case by sonication, then you can improve the luminescence, okay? Okay. What happens here? Okay, so then this is what we have, that they are much brighter than the normal ones, okay? And then what we do is we apply this to measure the temperature of an internal organ by using the lifetime. This is the fluorescent lifetime of these nanoparticles, silver sulfide nanoparticles, and obtained at different temperatures. You can see that the lifetime is strongly dependent on temperature. So if we measure the lifetime of these nanoparticles, we can know at which temperature the nanoparticles are. For example, you measure the nanoparticles, and the luminescence of the nanoparticles, and the luminescent lifetime, sorry, is 400 nanoseconds, means that your nanoparticle is at 22 degrees. The fluorescent lifetime is 200 nanoparticles, is 46 degrees. So we can do what we call luminescent lifetime thermometry. It's much better than using the emission spectra or to determine the temperature, because the emission spectra is affected by the tissues, okay? So these nanoparticles that are much brighter because we use sonication and we clean the surface are good for lifetime measurement. In fact, they are quite robust. There is no thermal hysteresis. I mean, you can have one nanoparticle heat up to 25 degrees, then go down, heat up to 45, then go down to 40, 25, up, down, up, down, up, down with the temperature, and you always obtain the same lifetime values. So it means that it's a quite robust system, okay? And also it's independent on the tissue. If the nanoparticle is under 2 millimeter tissue and under 4 millimeter tissue, the lifetime is the same. So the value of the temperature that you are going to measure by the lifetime doesn't depend on the tissue, okay? So it doesn't depend on the temperature of the tissue, and it's quite stable inside your body, okay? Okay, so we have a thermometer that is bright, can propagate through the tissues the light because it's working in the second biological window, and can measure the lifetime. It can measure the temperature by lifetime that is stable, is reliable, is robust. So what we can do, our idea is why not try to measure temperature of an internal organ? Up to now, all the work has been correlated with measuring, focus on measuring the temperature of a tumor that is on the surface or the temperature of the skin, but nobody has never tried to measure the actual temperature of an internal organ. And this is what we have. We have tried here because we have a bright nanoparticle. So then the light, even if the nanoparticles are in the liver, we can get the light out of the liver, okay? So the idea is the following: we inject nanoparticles, and then the nanoparticles will be accumulated in the liver. Then we will excite the animal with a pulse laser, and then we will collect the luminescence generated by the nanoparticles, and by looking at the oscilloscope, we are going to register the lifetime curve. And from the lifetime curve, we will estimate the temperature of the liver, okay? And then what we are going to do is to apply this methodology to describe or to do, how to say, diagnosis of an infection, okay? So we inject liposaccharide bacteria, it's a part of a bacteria, the animal, so we inject an inflammation or infection of the liver that causes inflammation, and then we are going to measure the temperature of this organ during inflammation, because we expect that during inflammation we will get some kind of temperature change. And this is what we have. This is the lifetime before injecting, the lifetime of the nanoparticles inside the liver, in the fluorescent lifetime. This is 200 nanoseconds. And when we perform the injection, we can see that there is a sharp decrease of lifetime. This induced is indicating that the temperature of the liver is increasing due to inflammation, okay? So, but because we know the lifetime versus temperature, we can translate this variation of lifetime into temperature of the liver. So we have that before injection, the liver was an almost constant temperature of 39 degrees. And when we perform the injection, the injection of this bacteria, then we induce inflammation. We start infection and then inflammation. And because of the inflammation, we increase the temperature of the liver. So we have developed a method to monitor the temperature of the liver to detect inflammation of the liver. And this is a completely contactless method because we are not using any thermocouple or any other technology. We are using the light generated by the nanoparticles, okay? Let me finish with the last work, which is the last method that I wanted to show you because the time is running and then I think I want to finish for the questions, is that we can improve the nanoparticles by what we call ultra-fast irradiation. Ultra-fast irradiation, it means that you have the nanoparticles, you use a femtosecond laser, and the femtosecond laser triggers the explosion of silver nanoparticles that reacts with the solvent and at the end creates a protective layer of silver chloride around the nanoparticle. And because of this protective layer, the quantum yield of the nanoparticles increase a lot. So the idea is you have your nanoparticles, you irradiate them with an ultra-fast laser, and this ultra-fast laser starts a chemical reaction, and the chemical reaction between the solvent and the and the silver atoms and so on, they create a protective layer surrounding a nanoparticle, okay? And because of this protective layer, we increase the brightness of the nanoparticle. You can see here, this is the infrared image of the nanoparticles. This is before and after irradiation. You can see that the color changed a lot. You can see here that the nanoparticles becomes much brighter. Indeed, the quantum yield that we obtain after 40 minutes of irradiation with this nanoparticle, with this laser, is close to 10%. Okay, and this allows us to obtain super high resolution of, for example, the vascular system. This is an image of the femoral artery after injection of silver sulfide nanoparticles, obtained with the commercial silver sulfide nanoparticles. You can see that you can observe that you can see that the artery is true, but it's not so. It's much more clear when you use this laser-treated silver sulfide nanoparticle because they are much brighter, and you can not only see the femoral artery, but you can see always the small arteries, and also here you can see the bone because the nanoparticles are also accumulated at the bone. So it means that you can use different methods to improve the illumination of silver sulfide nanoparticles, and these methods allows us to obtain super nice image like this image of the cardiovascular system with a super high resolution. Okay, so I want to close now because it's almost 45 minutes. The conclusion of this work is that silver sulfide, I mean, in general, infrared emitting nanoparticles are super interesting system for bioimaging because you can penetrate in the tissues. In particular, silver sulfide nanoparticles are very good for imaging, but also very good for sensing, in particular for temperature sensing. And the idea is that by measuring the temperature, you can not only, it's not measuring the temperature because you want to measure the temperature, because you want to control the temperature of a tumor, or you want to control or you can use the temperature of the liver for diagnosis, and so on. Okay, so this is basically what my talk and the message that I want to you to take home is that the use of nanoparticles, infrared nanoparticles, are promising for bioimaging, biosensing, and for biomedicine. Okay, and there are different methods to improve the quality of nanoparticles that can be done by using sonication, or can be used by using laser treatments, or by changing the synthesis process. Okay, so I want to finish with this image because it's the most representative example of how good can be the image that you obtain with these nanoparticles. So that's all. Thank you very much for your attention. I think that there are many questions here.
Okay, thank you very much, Professor Daniel Jaque. We have some question in the chat that I will pass to you. Our alumni, Alisson Torquato, he has asked a particular case for the comparison of these nanoparticles with rare earth ions nanoparticles. I would like to generate this question. He is asking that
I have here. So yes, the question is about is the reproducibility and repeatability of nanoparticles better in silver sulfide than in rare ions? No, not at all. I mean, if you are looking for the most robust, most reliable nanoparticles for sensing, for sure they are the rare doped nanoparticles, lanthanide doped nanoparticles. When you work with lanthanide ions, they are quite stable, they are quite robust. Here, these silver sulfide nanoparticles are okay, but in general, you have to be very careful when you work with the semiconductor nanoparticles because they are unstable. When you hit, you can change the surface or even the size, and because in some of them, the size also depends, the emission also, the fluorescence depends on the size, then you change the emission, and these are not reversible process. So the question is, no, it's better to use rare doped nanoparticles. But what is the problem with rare doped nanoparticles? Is that the brightness is super low. It's orders of magnitude lower than these nanoparticles. So in terms of stability and reproducibility are better. Also the spectral quality is better, but the brightness is a nightmare. I mean, it's very hard to work. It's hard to work with rare doped nanoparticles. Okay.
Okay, very good. Thank you very much, Daniel. And there are a couple of questions here from Professor Leonardo Menezes, that he is asking, in the sonication process for enhancing the nanoparticle emission intensity, the longer sonicated particles emit stronger, but lifetime measurements show longer decay times for these longer sonicated nanoparticles. Are these results compatible with each other?
Yes, because you can think in the following way. When you measure the fluorescent lifetime of a nanoparticle, is the result of the radiative and non-radiative decay rates. So if you reduce the non-radiative decay rates, then you obtain a longer lifetime, okay? Because the lifetime is 1 over the total, is the inverse of the total radiative lifetime, and total radiative decay rate. So if you reduce the non-radiative decay time, the fluorescent lifetime increases. So that's why when you sonicate the nanoparticles, the lifetime increases because you are removing non-radiative process, okay? And the total non-radiative decay rate is smaller, and then because the lifetime is 1 over the total radiative lifetime, the total radiative rate, and the lifetime increases, okay? So they are compatible. In fact, it's what we were expecting. When you increase intensity, you expect to have some increment in the lifetime.
Very good, thank you very much. So one more question here in the chat, that in the lifetime thermometry measurements, one measure fluorescence decay time. Which process generate this fluorescence?
What you have to do to that, you have your nanoparticles in the liver, for example, okay? And then you have to excite with a laser, a pulse laser, that promotes the excitation of the electrons from the valence band to the conduction band. And then the recombination of electrons and holes produce luminescence, and what you register is how fast is that luminescence, okay? So typically what you measure is, of course, you have to measure a number of events, but with this process, what you excite the nanoparticles to the conduction level, conduction band, and you measure how fast is the decay from the conduction band to the valence band. And then you obtain the fluorescent decay time, and you fit, and you obtain the lifetime.
Okay, in the same scenario, Professor Leonard is asking if this silver sulfate is a semiconductor material.
Mm-hmm. Sorry?
Is it a semiconductor material?
Yeah, it's a semiconductor material, but it's not a quantum dot, because the size of these nanoparticles is 10 nanometers, and the Bohr radius of this material is 2 nanometers. So the materials are larger than the Bohr radius, so there is no quantum effects. There is no quantum confinement. So it's a semiconductor, yes, it's a semiconductor. But it's not quantum effects in this material.
One more question here from Professor Adriano is asking if there is any side effect to the animal, to the mice, when doing these measurements.
No. I mean, this material in particular, I mean, there is always the issue of the toxicity of nanoparticles in the animals, and this material is particularly stable, and because of that, we have never observed any toxicity effects, and we have performed several studies of toxicity. We have measured the biochemical markers. We have analyzed it with detail the behavior of the animals, and there is no side effects. You have to think that the dose we are injecting is very, very low. We are injecting 0.100 microliters, a solution of 0.0 micrograms per milliliter, so it's nanograms. So the dose that we are injecting in the animal is super low. At these low doses, there is not side effects at all.
Thank you very much. Just to controlling the time, one more last question that Professor Carlos Jacinto is asking. Thinking in biological application, the emission spectra of the silver sulfide is very broad. Is there any problem for this material?
Yeah, I mean, it's it will be better to have a narrow spectra, because when you have a very broad spectrum, what happens is that in this very broad wavelength range, the properties of the tissues are not homogeneous. So there are the tissues distort the emission spectrum. This makes things difficult to make a good interpretation of the results. So it will be better to have a narrow emission lines, and then it will, because you can improve or optimize the system, and you can be very sure what you are measuring. Okay, when you have a very broad spectrum, sometimes you cannot distinguish very well between the contribution of the autofluorescence and things like that. So yeah, in fact, it's true. I mean, it will be better to have a narrow spectra, but who is providing you a narrow spectra? Lanthanide doped nanoparticles, and these are not bright enough for biological applications. So it's like balance between everything. So yeah, there is not an ideal system for bioimaging, of course.
Great. Thank you very much, Professor Daniel Jaque. In this talk, we have learned a lot. Thank you very much for to accept our invitation.
You are more than welcome.
And of course, there will be many questions here from my side, but I will pass personally to you. There will be some interaction between us. Thank you very much for your presence today. And just to control the time